So we just left off, we're talking about bases, and we said bases have a bitter taste. They feel very slippery, which kind of makes them a little more hazardous in the lab, if anything, because they can cause more accidents once they're spilled on the ground. But when put in water, they release, instead of hydrogens, they release OH negatives, okay, or hydroxides. And if you have an OH negative floating around in water, it would like to have a positive charge to match with it. And so we said they're also called proton acceptors because they're negative, they're looking for a positive to match up with, and so they might grab a hydrogen and join up with it. And if they did, then it would make hydrogen hydroxide, which is two hydrogens, one oxygen, is just another way of writing water. Hydrogen hydroxide is the same thing as water, or H2O. Okay? And so, OH groups that are floating around tend to be, we call them proton acceptors, because they're willing to accept that proton and make water. Now, not all bases have OH negative groups on them when they release it, but they do all want to accept, they give something that wants to accept a hydrogen, so they have some kind of a negative charge on them that wants to do that. Okay, and so they're all proton acceptors, but they definitely, if you see something like sodium hydroxide, you can guarantee that's a base, or potassium hydroxide. But there are some other things that may not have that, but if they still have a negative charge that becomes a proton acceptor, then basically they act as a base. And so just know if there is an OH in the formula, it definitely is a base, and if there's not, it could still be a base. Generally, acids, you notice, tend to have H at the first because they have to have a hydrogen. Okay. Now, there are some that may not have a hydrogen that give off a proton, but for the most part, they're going to start with a hydrogen. Hydrochloric acid, sulfuric acid, they're generally going to have an H at the beginning because that's the most common way for an acid to be formed. Now, if something is an acid, we say it's acidic. If it's a base, we say that it is basic, okay? And that just means base. But another word you may also hear along with base is the word alkali, like an alkali desert, or alkaline, like our batteries that are alkaline batteries. In fact, most A, AA, C, and D cell batteries are actually cells, not batteries, are alkaline batteries because they have a paste inside them that is a strong base. Okay, car batteries, on the other hand, are acid batteries because they have actually sulfuric acid in them. All right. Now, the word alkali comes from Arabic, alkali, and this basically means the ashes, because what they found is they burned their fire, there would be basic ashes, okay, the potash, the ashes underneath the pot, okay, and it contained a chemical called potassium, we recognize that, carbonate, okay, and this is also known as potash sometimes, and basically it's a base. Carbonate very often is a base. Sodium bicarbonate or bicarbonate of soda is baking soda, which is a base. If people have an upset stomach, they could take that and it would help neutralize it. Alright, so basically they used this, and they found that if they took this base and they mixed it with oils or fat, then they could make soaps from it. We talked about this, I think, a little bit earlier when we talked about soaps, but in this country, a lot of times soap was made from lard, which is basically animal fat, which they had from butchering pigs or whatever other animals they were eating, and they would mix it with lye, which is a very strong base, and they would make lye soap. And if you ever talked about getting your mouth washed out with lye soap, apparently lye soap was really nasty stuff, and usually it probably wasn't neutralized. It was probably still kind of strong, bitter, and basic, so it's not very pleasant. So that was a pretty bad thing to have to do that. Okay. Now, if we want to measure this, how do we measure how much of an acid or a base something is? Well, as we talked earlier, we said there are strong bases, weak bases, some are diluted, some are concentrated. So how can we come up with a number that would tell us how strong they are? Okay, and basically that's what's known as pH. Okay, the pH of a substance tells us how much of a acid or a base something is, and we measure that on something called the pH scale that we'll look at here in a minute. All right. But basically pH, the P, notice it's lowercase, and it's always lowercase, and because it means concentration. Okay, it's a symbol for concentration, and what it means is concentration of H's. Capital H is a symbol for hydrogen. So basically we're saying, what is the concentration of hydrogen ions? Okay, now you would think that that means that the bigger the pH, the more hydrogen ions you have, but as it turns out, that's not exactly true. Now, explain how it works. To explain how it works, let's look a little bit first of all at the pH scale. This is the pH scale, and the lowest number is 0 because, okay, and that would be it. At the highest end of the scale that we normally use is 14. All right. Now, halfway in between would be 7. All right, and generally speaking, if something has a pH of less than 7, we say that it is acidic. So these are all acids over here. All right, and as it goes towards 0, it becomes more and more acidic. As you go toward the middle and go this direction, it becomes more and more basic. These are all bases, and as you go this direction, it's going to become more and more. So the strongest bases are over here. All right. Well, it turns out that pH is the negative log of the hydrogen ions. Now, what does that mean? Well, first of all, the negative log means, for example, let's say that you had 100 ions of hydrogen in a certain amount of liquid. All right. Then this would be 10 to the 2, okay? But the negative log of that would be 1 over 10 squared, all right? And if this was the pH of the substance, this number is the number that we say their pH is. So we'd say this has a pH of 2, which means that it has 100 hydrogen ions. If it has a pH of 3, it would be 1 over 10 to the third. Okay, all right, and so this is 1 over 100. This is equal to 1 over 1,000. So it's less. It's becoming a smaller number. As this exponent gets bigger, it makes the denominator bigger, so it makes it a smaller amount of acid or hydrogen ions, which makes it closer to 7 and makes it less strong or less powerful of an acid because, or less acidic because it has less. If you had 6, that would be 1 over 1 millionth. Okay, so 1 over a million, and so it would be much less so than this. Now, the other thing, since log, we're looking at exponents of 10. That means when you go from here to here, it is 1/10 as strong. Or if you're going from an acid with a pH of 3 to a pH of 2, it's 10 times stronger. Just depending which way. It's 1/10 as strong. An acid, if you go that way, is 10 times as strong an acid as you go this direction. All right. If you went to 1, from 3 to 1, a pH of 1, instead of just being 20 times, it would be 10 times 10 again, so it would be 100 times stronger. So every time the number of the pH changes, it changes by a power of 10. So this would be 10 times stronger than that. This would be 100 times stronger than a pH of 7. Something with a pH of 4 would be 1,000 times, 10,000 times, 100,000 times, 1,000,000 times, and then finally it would be 10 million or whatever. Okay, but basically you see as it goes this way, you're changing the exponents of 10. Okay? All right. Now, as you go this direction, all right, that number continues to get smaller until you get over here where it'd be 1 over 1, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2. Now that throws off my decimals, but okay, you get the idea. It's going to be a very, very small amount of hydrogens that are present in something with a base with a pH of 14. All right. Now, if you got all the way to 0 down here, that would be 10 to the 0th power, which would be 1 over 1, which would mean all you have are hydrogen ions, and that's as much as you can get. You can't get more than 100% hydrogen. This number technically could keep going because you could have even lower concentrations than this, you never get to zero. You can just keep adding zeros on and making the percentage of hydrogen smaller and smaller and smaller. So it keeps on going forever, but we're not going to worry about that. And most things fall less than 14, so we just say it goes to 14. All right. Now, instead of writing, for example, this is a pH of 6 as 1 over 1 million, it would be the same as 1 times 10 to the negative 6. Okay, that's basically the same thing. So you may see the pH written as that. That would be something with a pH of 6. Okay, because a negative 6 means it's 1 over 10 to the 6th power. All right, and so that would be the same thing as 1 over 10 to the 6th power. Okay, and that's basically what we said this was down here. So it's the same, a different way of writing it. All right. Now, let's talk about water for a second. We haven't talked about water. Is water an acid or a base? And most people say, no, it's not an acid or a base. It is neutral. It has a pH of 7. And that would be correct. But that may miss a little bit of understanding about it. Let's think about it this way. If you have water, we said water could be written as HOH. Could water become acidic? Well, we said most acids start with what letter? Hydrogen, because they're going to give off a hydrogen. If you write water this way, and this is really perhaps a better way to look at what it actually looks like, or how it acts or reacts sometimes, you do have an H. All right, so it could, this hydrogen could come off, and in water you could have a whole bunch of hydrogens floating around. But, on the other hand, when this takes off and comes over here, what do you have left? Well, you have an OH negative, or hydroxide, which makes it a base. And at any given time in water, some of the water molecules are separating, just like this. They will do this. And what that means is you have hydrogens and you have OHs floating around, acid and bases molecules floating around, ions floating around. But for every hydrogen you have floating around, you're also going to have exactly the same number of hydroxides floating around. And so water is in fact neutral. There's always going to be the same number of hydrogens of oxygen, which is what at 7 means. But it's not it's because it is an acid and a base. Water can act like an acid or it can act like a base. When we put hydrochloric acid into the water, one of the reasons hydrogens come off because the hydrogens can join up with these other things. So basically water is both an acid and a base, but it's going to have the same number of hydrogens and OHs. But when you put hydrochloric acid in here, here's what I was trying to do, and now it comes off, now you've thrown it out of balance and you've added more hydrogens. Or conversely, if you add sodium hydroxide and it has OHs coming off, then now you've tipped the balance in time of the OH. So pure water is always going to be 100% neutral at 7. But, just for the record, you don't ever have pure water. Water almost has other things dissolved in it, and those things may or may not affect the pH. Now, what are some examples of acids and bases? This is obviously a very partial list. There's all kinds of acids and bases, but here are some just to give an idea of how strong they are and things like that. For example, a very concentrated acid would be HCl. It can obviously be diluted to make it however strong you want, so not all acid is equally, but it can be pH of extremely low. Okay, battery acid, also lemon juice. Okay, vinegar somewhere in here. Soft drinks tend to have phosphoric acid and other acid. I know, like Dr. Pepper has phosphoric acid, but they have different acids in them. Obviously, citric acid and things like 7-Up and things like that. Beer slightly, tomatoes are slightly acidic, coffee, urine, rainwater is usually slightly acidic because it hits carbon dioxide on the way down and makes carbonic acid. Milk is even less so. Saliva is pretty close. Pure water would be neutral. Then going down the acidic side, your blood is, or basic side, your blood is slightly basic, 7.35 to 7.45, so just slightly. And seawater, interestingly enough, is almost about the same concentration. All right, baking soda soda comes a little farther. Soaps that we use, ammonia, hair removers getting pretty strong base, oven cleaners getting pretty strong. Chlorine was be down here and they're very strong with if it's